Okay, welcome back to BME 2315. In this lecture, we'll be covering multidimensional optimization. So in the past lecture, we discussed three types of optimization: golden section, steepest ascent, and Newton's. And all of those were applied for cases where we had a single variable. However, many realistic biomedical engineering problems have multiple variables for which you need to optimize. Think of about something as simple as speed versus cost, or speed versus reliability. There are lots of things that we need to optimize multiple variables at once. And so in order to tackle those mathematically, we're going to need to turn to multivariate versions of steepest ascent and Newton's method. And to do that, we need to be looking at multivariate calculus. So let's take a quick detour or a background and refresher about what some of these things look like. The first that we'll talk about is the gradient of a matrix. So the gradient of a function here is telling us how that function changes with respect to each of the independent variables. And so, for example, on the top right, we use this upside down delta to denote the gradient operation, and that is equivalent to taking the partial derivative of f with respect to x and the partial derivative of f with respect to y. So if we have this example problem here on the top, then if we take it with respect to x, you get y and then minus 6x, and so that's why y minus 6x is up here. If we then, for the bottom, have to take that partial derivative with respect to y, and so we get xy goes to x plus 4y goes to 4, and then this term goes to minus 2y. So that's how we're taking the derivative with respect to that. If then we want to evaluate the gradient at a specific location, then we can plug in the various values of f. And so in this case, it'd be -1 because we have a negative y, minus 6(1), and this is 1 plus 4 minus 2, -1, equals minus 7 and 7. So that's evaluated at this point of 1, -1. And so what that looks like is that it's telling us it's pointing uphill to say it's steeper if you go that way. That's what the gradient is telling us. Okay, so the next type of operation we need to be able to deal with is the Hessian matrix. And the Hessian matrix is basically taking two partial derivatives with respect to those independent variables. And so we'll take a look at how that works. The Hessian matrix is operating on a single function with two independent variables. So we have x1 and x2. And so to help us understand how that works, we've got a simple function here on the right hand side, and we'd say that df dx equals 3 minus 3x squared plus y squared, and df dy equals minus 3y squared plus x plus 2y plus 2xy. So those don't get plugged in yet because we're going to have to take another round of differentiation. So that's just the first derivative, and now we need to be able to take the second derivative. And so I'll show that down here at the bottom, where if you take the second, if you again take the derivative of this term df dx by x, you're going to be left with negative 6x. And if you again take the derivative of this df dy, with respect to y, you'd get negative 6y plus 2 plus 2x. And in the corners, you get 1 plus 2y. It doesn't really matter whether you take this with respect to x or this with respect to y, or this with respect to x, or this with respect to y, you'll end up getting the same answer. So basically, these Hessian matrices are important for indicating what type of basin that we're in. So as you see here, that if the determinant is 0, and you've got the curvature being less than 0, then it's a local maximum. Or if the second derivative is greater than 0, then it's a local minimum. Okay, so we'll be using these gradient and Hessian calculations in the in our implementation of Newton's method. So let's, before we do Newton's method, let's look at the little bit simpler one of multivariate steepest ascent. And so in the single variable steepest ascent, we had xi plus 1 is xi plus h f prime xi. And the shape of this method is just the same right here. It is simply that we are using the gradient of f instead of just the derivative of f. Okay, and so we're just going to do a single example here, starting out with x1. So x1 is going to be x0 plus h delta f x0. Okay, and our x0 location is at 1, negative 1, as you can see right here. And we're going to take a step size of 1/7. That's 1/7. And when we take the gradient of f, so this is the gradient of f, and when we take that with respect to x and then y, and then plug that in, we should get negative 7 and 7. Which takes us to 0. Okay? And then let's do one more iteration of this. If we have then x2 is given by x1 plus our step size times the gradient of f at x1. We're already at 0 plus 1/7, which is our step size, 1/7, and 0 and 4, which is our gradient. Remember, we're just using the gradient that we have up here at the top right. Equals 0 and 4/17. So basically what that looks like is that we started at 1, 1, or 1, negative 1, and then we jumped to 0, 0, and then we jumped up a bit to 4, 1/7. Okay, so that's the multivariate version of Stevens' ascent. Now let's take a look at how to do that with Newton's method. So Newton's method is going to be kind of conceptually similar. We're just going to have to be using this Hessian equation that we have on the top right. So I'll start by writing that out. So the Hessian, you'd start by looking at the gradient matrix and then take each of the derivatives. And so the Hessian matrix ends up being -6, 1, -2, and 1. Because here you're taking the first derivative with respect to x, and then here you are taking the first derivative with respect to y, and so on. Okay, so that's the Hessian matrix. And then we're going to plug this into our overall equation. Oh, first off, we need to know what the gradients are. So the gradient of x0, so kind of evaluating this at x0 equals -7 and 7. And the inverse of the Hessian, notice that you're going to have to take the inverse of the Hessian right here. And so you can't do that very easily by pencil and paper, but you could do that on a graphing calculator, or you could do that in Python. And so this Hessian matrix, I'm sorry. In this case, this is just a 2 by 2. So this 2 by 2 is actually quite easy to take the inverse of. So the inverse of that is 0.1818, -0.09, five. Okay, so that's the inverse of the Hessian. And then we can apply that, kind of putting all these little pieces in together, so into the multivariate Newton's method, and say that x1 equals x0 minus the inverse of the Hessian at x0 times the gradient of f at x0. That equals 1 minus 1 minus this inverse matrix so 0.909 and negative 0.5455 multiplied by -7, 7. Okay. And if you multiply those out, you should get something like 0.3636 and 2.1818. Okay, and so you can see just how good of a job this did, is that it went exactly from this spot right here all the way to the top of the mountain in just one shot, and that this is very close to the analytical solution. So this really shows the power of multivariate Newton's method. So So just to leave you here with a few tips, if you try to take this to even more complex problems, there are many cases where you cannot analytically compute the derivatives, as we did here in an example. And so in those cases, you need to use finite difference approximations to compute them. So it makes the solution quite a bit more complicated than what you can do by hand easily. And finally, there are other numerical considerations involved in these methods, such as the matrix inversions that we just showed you. That was just for a 2x2, but for a very large system, they can become very expensive computationally. And so you need to then look for ways to speed up the speed at which the processing happens. And in general, the Newton's method is going to converge much faster than steepest ascent when it's near the maximum, just like whether we're talking about the 1D version or the multidimensional version. It's going to go much faster than the maximum, but it has the limitation that it may diverge very far. And so it's very important to watch how many iterations it took to show that, make sure it hasn't taken a very large number of iterations, and then plug in the values that you get to make sure that you are in fact at an optimum, at a maximum, rather than something that is more spurious. So with that, thanks for your time. I hope that was helpful to you. Take care.